So in this series of videos, we're going to talk about the time value of money. And before we get started, just to let the people understand that are viewing this video, is that my courses are provided a worksheet that will help them solve some of these problems. So the actual problems can be solved with formulas or financial calculators. There are Excel formulas that you can use, but those are all provided in class. So when you see a spreadsheet here, I want you just to recognize that this has been provided to my students. So the time value of money is probably one of the most important things, quite frankly, that a person needs to understand, right? We need to understand that the value of dollars change over time. In this example here, when I think about when you were a youngster, you said, Mom and Dad, I need $20 to go on a date, and you say, well, $20, oh, good Lord, when I was a kid, you get that type of a scenario, and it's a true, real scenario when the value of money loses its ability to buy things over time. So $20 20 years ago bought a lot more stuff than $20 today. So our purpose is to try to figure out how we can visualize this. How can we discuss the changes in value over time? If you think about making business decisions, right? All business decisions are about the future. And one of the most important things we're interested in is the cash that we're going to receive in the future. So we need to have a way to analyze the importance and the changes in value over time so we can make some comparisons and ultimately make some good investment decisions. So one of the easier ways to do this is to create something called a timeline. It just makes an illustration or shows how things change. The timelines always have a negative value for investments or money going out, right? Also, timelines start at time 0. So if you invest your money today, it sits there for a whole year. That's why the periods marked out here start at 1 year out and reflect a year's growth in an investment. So when we're looking at this question of time value, we can be looking to the future or we can be looking to the present. So the concept of something called compounding is where you take cash flows that you expect to have or to pay, and you see what value they will grow to in the future. The present value says we think we're going to get these cash flows in the future, and we would like to see what they are worth in today's money. So we're either moving dollars forward to see what they would buy in future dollars, or we're bringing them back to see what they would buy in the present dollars. As I mentioned, right, there's formulas, financial calculators, spreadsheets, right? You'll see formulas in here. Again, some of them get a little bit complicated, but working with Excel spreadsheets is a very easy way to try to solve these problems, quite frankly, without doing any math, right? So what will happen throughout this course is that in addition to this video, there are also videos that explain how to solve all of these problems that are provided to classmates in the program. As I mentioned a little bit earlier, in order to find a correct answer, right, financial calculators and the computer, they require the cash flows be entered with the right sign. So cash inflows, money that you're receiving, are indicated by positive values, and cash outflows are obviously indicated by negative values. So if the money is coming to you, it's positive. If the money is coming out of your pocket and is being invested and placed somewhere else, that is a negative cash flow stream. There are three basic patterns of cash flows. we will start talking a little bit about single amounts, sometimes referred to as a lump sum. So we will look at this, we'll see what its value, future value, what is it worth in today's money, and we will take an investment today and move it forward, as we will do with all of these. An annuity is a cash flow stream that is an equal cash flow for a certain period of time. It obviously then requires a payment of some sort. So these are equal payments for a certain period of time. And of course, a great example of an equal payment cash flow stream is a loan, right? So if you borrow money for a mortgage on a house, you know that every month you have an equal payment for the life of the loan. A mixed cash flow stream is really a more business-oriented kind of an example, but this just shows that over time, cash flows, there might be many of them, right? More than one, so it's not a lump sum cash flow, but they might be many cash flows, but they are not necessarily equal in amount. So let's first start talking about future values, right? So future value is a value sometime in the future. Things that we need to know. We need to know something about what rate of return we could earn on this money. We need to know the time frame. So we can apply a formula to this calculation. This, quite simply, is an investment question. If I put money in the bank today and it stays there for 10 years, how much will be there at the end? Now, the concept of compound interest is where interest is earned not just on the given deposit, but also is you earn interest on the interest itself. So this is interest earning interest concept. The principal is obviously the amount that is invested in the beginning. So let's talk a little bit about the variables, right? So there are only X number of variables. In fact, the time value of money questions, although they're not always simple, are essentially algebra questions. You know everything you need to know except the thing you're solving for. You do the math and can ultimately get the answer. So PV0 is the present value or the beginning amount. R is the interest rate. That's the interest rate per year. FV subscript N is the future value at the end of certain period of time. N is the number of years. A is an annuity. So another way to say this, an annuity is a payment. So we can find PVA, which is the present value of an annuity, and we can find FVA, which is the future value of an annuity. And the letter M, and I'm not sure why it's M, but M represents the periods per year. We'll talk about this as different compounding structures present themselves. We'll talk about the impact of that on money and how money grows. The compounding frequency, what we've just been talking about really, can be more than once a year, right? So if you compound more frequently once a year, essentially you're calculating interest on a more frequent time frame. So we have to adjust the interest rate per year. So again, if you had a 12% interest rate and you were going to calculate interest every month, 12 divided by 12, every month interest would be charged or earned at 1%. But as soon as you calculate interest once, that then grows per period for the rest of the investment's time frame. So again, we need to adjust the frequency of calculation of interest so that we can understand the full benefits of the time value of money concept. So again, we have the following notations here. We've already talked about these variables. There's a general formula for future value. You take the present value and you multiply it by 1 plus the interest per year to the nth period. Now, If m is greater than 1, then we have to incorporate m, the compounding frequency, in the formula. If you're using Excel, it's a very simple formula. It's equals the future value. Then you have the rate, comma, number of periods, payment. Again, this is a lump sum payment. It would be this is for annual payments. So that's, for this example, might be 0. The present value is the investment that you make. And then time or type is the whether the cash flow occurs at the beginning or the end of the time. And we'll discuss those as we go along. So the higher the rate of return, the faster money grows. So again, as you can see here, we have time going to the right, and each one of these bars or lines represents a growth rate. So if you notice the end value for the green line, which is at 18%, right? That's compounded monthly, I'm sorry. At 18% is the blue one, compared to 14%, which is the yellow, and working your way down, you can see that as interest rates go up, the value grows quicker. Likewise with time, the longer time you have, the greater the amount of money there is. And finally, the greater the compounding frequency, the faster the growth. The difference between the blue line and the green line is that the blue line is compounding interest monthly rather than calculating it annually. So let's look at an example of future value, right? Fred saves a lot, places $1,000 in a savings account that pays 7% interest compounded annually. He wants to know how much money will be in that account at the end of 5 years. So we can use the time value of money table or worksheet. That's this worksheet here. You could also use the formula, right? We talked about the formula earlier. You input the negative $1,000 here for value, 7% interest, time in years is 5, compounding frequency is 1. So the future value of this is $1,402.55. Again, slightly different value than up above, but they're in the ballpark. So we do have to, from time to time, worry about rounding errors. Again, using this formula, right, probably didn't account for all the rounding that's taking place in the actual worksheet itself. So essentially, this is saying what? $1,000 grows to $1,400 and some dollars in 5 years if you can earn 7% interest. So if your parents invested $1,000 the day you were born, and they could earn 10% on invested dollars, how much would you have now? So what I suggest you do is quickly, open the worksheet that you have at your disposal if you're in this class, and plug in the numbers to solve this problem. So if you invested $1,000, the present value would be negative $1,000. 10% is the interest per year. And now how much would you have now? Start assuming that you're only 18 years old. So that means time equals 18. So how much money would you have? That amount of money would grow to, if you see down the notes below, $5,559. If you kept it in there from the time you were born till the time you turned 65, you would have almost $500,000, $490,370. What would be that answer if you compounded monthly? So we can change this example just by changing the numbers in the table, obviously. So in this case, first of all, we changed from 18 to 65 in years. And now this time we're changing the compounding frequency from 1 to 12. And if you could get interest compounded monthly, now we're talking about almost $650,000, which is $150,000 more for the exact same investment. So compounding frequency is just as important as the amount of money that was being invested. So that's the stop or the end of the first video. We're going to work our way through talking about different kinds of cash flows, different types of decisions that we can make using the time value of money.